Swayam Prabha. Digital India. Educated India.
Friends, so let us go to another topic of gradually varied flow. Of course, a part of that topic we have already discussed in the last class, and today we shall be discussing on, that is, gradually varied flow and its computation. Of course, before going to the computational aspect, we need to know some of the finer details of the gradually varied flow, and as such first we will be covering that part and then only we will be going to computation of gradually varied flow. In the last class we did discuss about the control section, and then we were talking how a supercritical flow get affected only by the disturbance that we create at the upstream of that, and subcritical flow gets affected by the disturbance created at downstream of that flow section. So, let us go to some more detail of that particular issues. Well, let us start with the fact that many of us, all of us rather, we have seen that, say, if we have a still water, like this, and say this is a still water, and there if we make any disturbance, say we are throwing a stone into it, or some, if we talk about say larger size of disturbance, some explosion can be there. Well, whatever may be, suppose if we throw a stone here, then this part get disturbed, and then what we see, the waves are moving like this, okay. With time these are moving like this. So, this is a common things which I think almost all of us have seen that. Now, this disturbance that is moving in the form of a wave, and that the speed at which the wave is moving relative to the speed of the media, that is, suppose when our water is in static condition, if it is a pond, then of course that media is not having any speed, and then any velocity rather, and then when wave is moving over that, means its absolute speed of the wave is equal to the relative speed, and that speed of the wave we call as celerity, okay. Now, say in a channel, when it is, suppose it is in rest, say it is in rest, so say it is moving in this direction with a speed c, and of course if this is moving in this direction, it is moving in the opposite direction also, in all this direction, in all around, in all direction it is moving with a speed c, that is one. Now, if we give a velocity to this media v, suppose now let us talk about a channel, where this fluid media is flowing with a velocity v. Now, if we create any disturbance at this point, and suppose that wave is moving with a velocity c in this direction, then of course there will be motion of this wave in the upstream direction as well. Now for supercritical flow what will happen, and for subcritical flow what will happen, that we need to see. Now for supercritical flow, we have that this velocity v is greater than the velocity c, that is celerity c. Okay. So in fact we got that Froude number is greater than equal to 1, and Froude number is nothing but v by root over gy is equal to 1. And it can be shown that for rectangular channel this root over gy is nothing but say c. So we can write v by c is equal to 1, is greater than 1, rather we are writing all this as greater than 1. So this is greater than 1. That means what we can write, that v is greater than c. That is what we are writing from this part. Okay. Now as v is greater than c, suppose for example let us take, if suppose v is equal to 3 and c is equal to 2. Now this wave is moving at a speed 2 relative to v, that we need to know. And now what will be its speed in the opposite direction, because the media is moving. Opposite direction means if I talk about the upstream direction of this point, then as v is 3, c is equal to 2, suppose c if it is trying to move in this direction also it is 2, so it will be the relative speed if I, or the speed in this direction if I write, that will be, that means if we just think that fluid is moving and the wave is also moving with that, then what is trying to move upstream is also moving. Suppose 3 minus 2, that means what we will have, that 2, say 2 is in this direction and in this direction it is 3, so 2 minus 3, it will be moving, total net speed of this will be say 1 in this direction. Net speed of the wave which is trying to move in the opposite direction, net speed of that wave will be 1 in the opposite, in the downstream direction. So in reality when you are creating a disturbance, and net speed of this in the downstream direction will be of course that is which is trying to move in the downstream, this part will be again absolute will be 3 plus 2, absolute will be 3 plus 2 in this direction, and which is trying to move, the wave that is trying to move in this direction, that will have 1. So what we can say, that if we create any disturbance in supercritical flow, it is not at all propagating in the upstream direction. This disturbance is not propagating in the upstream direction. It is moving, all the disturbance is, net movement is always in the downstream direction. So that is not affecting the upstream flow. Whatever disturbance you create, that entire disturbance is moving in the downstream direction. Entire disturbance is moving in the downstream direction. This is moving with 5, this is moving with what, but entire disturbance is moving in the downstream direction. And disturbance is not propagating into the upstream direction. In unsteady flow situation, when we will be discussing characteristic equation, then we will see that these characteristic curves are always in the positive direction in case of supercritical flow. Well, that part we are not discussing here. I am trying to explain this in terms of a very simple situation which is where which is very familiar to us. Well, and that's why the statement that we passed in the last class, that is, in case of supercritical flow, any disturbance created at any section will not affect the upstream of the flow. So say if a supercritical flow is coming, suppose this is supercritical flow, suppose it is supercritical flow, then this flow is coming. If you are creating something, that is not influencing this flow, it is coming due to some slope, due to some discharge here, say for this slope, for this discharge it is coming, it will flow as it is, it will flow as it is. This disturbance is not influencing this one. But in case of subcritical flow, in case of subcritical flow, you can see in case of subcritical flow, V is less than equal to C. V is less than equal to C, because say we have Froude number is less than equal to 1 in case of subcritical flow. So, as V is less than equal to C, say now for subcritical flow, if I draw this one, it is coming like this, and say it is moving with a speed say 2, and then C we are creating a disturbance here, and that disturbance may be wave or whatever it is, then it is moving with a speed say 3, it is celerity C is higher than the velocity V. So, this is what I am drawing V, and this is what I am drawing C. Now, relative speed in the positive direction and in this direction, if we want to see absolute speed rather, then in this direction also it is trying to move with a speed 3, and so absolute speed of this wave in the upstream direction will be that this 3 minus 2, so there will be a amount of 1 velocity is there in the upstream direction. So, always there will be some amount which is moving in the upstream direction. So, any disturbance if you create here, that will be moving in the upstream direction, and as it is moving in the upstream direction, this will influence the flow of the upstream part if it is subcritical flow, as P is less than equal to C, if it is P is less than equal to C. And what about the downstream point, that when this flow is moving, in case of subcritical flow, when suppose the flow is moving with a velocity V and C is very faster, so disturbance you are creating is moving much ahead of that. So, this flow as such will not be affected. This is moving with a velocity V, it is moving, C is faster than this, so wave is moving far ahead of the velocity. So, this is not getting affected in the upstream part, downstream part. So, at downstream this will not be affected as such, and control section, I mean there will be influence, but so far the control is concerned, that in case of subcritical flow we get it on upstream downstream side, and then at upstream this will influence the upstream flow. This is that I have tried from my side to explain with some simple case of example and from physical understanding of the situation, which really shows us that why the control is at downstream for subcritical flow. If you do something on downstream, this is influencing the upstream. So, if we want to compute subcritical gradually varied flow, then we should see what is there at the downstream point, that is suppose the control section, we are getting that value, and that value is influencing the entire flow. So, we will have to start computing from the downstream side. This is one way. And then in case of supercritical flow, if we see that is why the what is the important influence of the control section. Suppose if we talk about well, let me show you one example here. Say this is a mild slope, this is the mild slope, SB less than equal to SC. So, critical depth line is this one CDL, normal depth line is this one NDL. Now, there is a free fall. So, free fall means also a control section. Okay. There this free fall will decide what the depth of flow here it will be. Let me extend this line CDL. So, we know that in nature the flow will be moving based on this slope, based on this bed slope, the flow is coming as uniform flow here. And then when there is a free fall, overfall, so this drop, canal drop or whatever it is there. So, the flow will have to go like this, and then actually this water profile will start from this point and it will be coming here and it is meeting. So, this profile is basically M2 profile. Now this profile is moving like that and it is meeting the CDL line normally at this point. Okay. Now, so at downstream point, this is also called brink depth or end depth, and from practical point of view, as hydrostatic pressure is not prevailing here, that assumption was there for hydrostatic pressure. So we can see that some investigator analyzed what is that brink depth or end depth is not exactly equal to critical depth. There are some difference, but for approximately we can consider that this is equal to critical depth. Okay. Now from here we are starting say critical depth, and this is our downstream point. Now, so as it is subcritical flow, because depth is here, so flow is greater than critical depth, all entire the flow profile is greater than critical depth, so it is subcritical flow. So it is subcritical flow. So in case of subcritical flow, suppose we try to compute this profile. Compute means we need to know at what x, suppose this is x and this is y, at what x what the y value is, at different x what will be the y. Now for our purpose we know that at upstream end the profile meet the NDL asymptotically, but at what distance, that we do not know. What will be this distance, that we do not know at what point it is meeting. So where from we will start our computation. Well, and that's why one thing we can do, that we can start from uniform flow and then we can start computing in this direction. We will compute till the flow is just higher than critical depth, because at critical depth this cannot be computed because our slope become infinite and that is not computable. So just above the critical depth we can compute and we can stop. That way we will be getting what is the total length that we can get. But another way is that we can start computing it from just above critical depth here. At this section we can start computing. That first point, suppose we know at this point just above critical depth at x equal to say 0 we can take at this point, x equal to 0. And then we can start computing in this direction, that at different x what will be the y from the equation of gradually varied flow. Okay. And we are computing, and then we can stop computation when our depth will be just y is just a little less than, or when it approaches yn. Of course, exactly at yn we cannot go, it will take, it will be uniform flow, so it will, we need to stop it just a little less than, when it is just little less than yn. Well, so this is the condition of flow when it is a subcritical flow, and that is what we are talking about control at downstream point. Now if I take the same shape, if we take the same bed condition, that is, but it is suppose steep slope, it is steep slope and it is like this. There is a drop, and if it is steep slope, that is SB is greater than equal to SC. Well, SB is greater than equal to SC. Now if SB is greater than equal to SC, then we can have our normal depth line. Well, first let me draw the critical depth line. Critical depth line is here, CDL, and as SB is greater than SC, normal depth line will be below this one. This is normal depth line. Okay. Now in nature, if we do not make any disturbance, then that flow depth will be coming along the normal depth line. So it is coming like this, and at this point it will be falling like this, it will be falling like this. Now as this is a supercritical flow, this flow will not be affected by the disturbance that is created at this section. So what will happen? The supercritical flow will be moving straight this way, and then it is coming up to this point, and then it is dropping like this. So there will not be any gradually varied flow forming at the upstream point here. At the upstream point, we will not be getting any gradually varied flow if the supercritical flow is forming here, and that will straight continue and it will fall like that. So, that is how the knowledge of control section is required. Generally, feeling may comes that okay, whether it is supercritical flow or subcritical flow is coming, it will be dropping like this, but no, in subcritical flow only it will be coming like this, it will be dropping like this, but in supercritical flow this will go straight and then it will fall like this. So, this sort of understanding will be required while computing gradually varied flow, and of course, analyzing different situation under gradually varied flow. Well, now with this understanding, we can go to another topic, that is gradually varied flow over series of slopes. Series of slopes mean varying slopes. Say mild slope is there, then in the nature it has changed to a steep slope, or maybe mild has changed to milder slope, I mean further flatter. So, that sort of combinations are very common in nature, and rather in nature we will be getting this sort of combinations only. We will not get a channel with say uniform slope all through it. So, in that sort of channel, how we can compute gradually varied flow, or first for computing gradually varied flow, first we must know that what sort of gradually varied flow profiles are forming, and once we know that this sort of gradually profiles will be forming there, then only we can go for computation of gradually varied flow, and before that we cannot. So, understanding of that part is definitely important. And there can be different combination of slopes in series. Say there can be a steep slope coming, and then that steep slope is changing to a mild slope. Say from the hill the slope is coming like this, it is a hill and then it is becoming flat. Okay. So, this may be a steep slope and then this is becoming a mild slope. There can be some other combination that a mild slope is coming and then it is again changing to mild slope, but it is steeper than this mild slope. Okay. That means this particular part is milder, we can say that this is milder and this is mild. Well, now here we shall be discussing some of such cases, and why we are taking some of such cases only, that is we are taking this sort of case, the mild to milder. Mild to milder means first it is coming like this, it is a mild slope, SB is less than equal to SC, then it is becoming still milder. Here also SB is equal to SC, less than equal to SC, but it is flatter than this one. Then we can discuss milder to mild, that means this case. Then we can discuss mild to steep, say a mild slope is coming, then it is becoming steep, mild to steep. Then we can discuss steep to steeper, a steep slope is coming, a steep slope is coming like this and then it is becoming further steeper. So, it will be steep to steeper. Okay. And then we can discuss steeper to steep, that means it is otherwise also steep and still it is becoming steep, but this is steeper and this is steep. So, different combination we can have, and we are particularly choosing here under the gradually varied flow chapter to discuss these different slope. The reason is that we out of all these you can see we are not talking about this particular case now. The reason is that here in this part the slope is steep, means water will be coming as supercritical flow, and then here it is mild, means flow will become subcritical. So, when the flow changes from supercritical to subcritical, then the phenomenon that take place is called hydraulic jump, and we are yet to discuss hydraulic jump. So once we will be covering the hydraulic jump chapter, and then only we will be able to appreciate this change, we will be able to understand the flow situation or flow profile of this type, where along with the gradually varied flow there will be some portion of hydraulic jump. And right now of course it may be little bit difficult because we are yet to cover the hydraulic jump topic, and that's why we are excluding those situations. And just as a typical example, we are giving some of these examples. So let us take first this mild to milder. Well, say it is a mild slope coming, mild slope and then it is becoming further milder. This is not horizontal, this is also mild slope, but it is milder than the existing one. So this is also SB is less than equal to SC, here also SB is less than equal to SC. Now if I give this as SB1, this is SB2, then we can write that SB1 is less than equal to SB2. Oh, am I wrong? Yes, I am wrong. SB1 is greater than equal to SB2. SB1 is greater than equal to SB2, because this is comparatively steeper than this one, but of course in mild slope portion. Now supercritical depth is concerned, let us see what sort of profile it will be during the entire flow portion from here to here. Okay. So supercritical depth is concerned, YC, okay, let us consider this as rectangular channel. Then so for critical depth is concerned, we know that this is equal to Q square by G whole to the power 1/3, Q square by G whole to the power 1/3. Well,